Good morning everyone, my name is Preeti. I work as a kernel developer in the Linux Technology Center of IBM. I've been working there for the past 1 year. Off late I've been working on the power aware scheduler very closely with the community, and I'll be speaking, my focus will mostly be on that. So although the topic does say the overview of the current approaches to the Linux scheduler, I will be focusing more on the power aware scheduler because it itself will take a lot of time. So I'm sorry if I'm disappointing you by not giving you all the approaches. I mean, as of now, at least in the current Linux scheduler, the more focus is on the power efficiency of the scheduler and a little bit on the scalability of the scheduler. Therefore, I will be focusing more on the power aware scheduler and the power efficiency, and brief you upon the scalability. So this is how my agenda stands. I will be introducing Linux scheduler so that it's easy for you all to understand what the power aware scheduler is all about, and the remaining 4 topics will be a deep dive into the power aware scheduler, and finally I'll be concluding with the other efforts which enhances the power efficiency of the Linux scheduler. So these are the 2 primary goals of the Linux scheduler. The completely fair scheduler, or the CFS scheduler, was designed to meet the first goal. It has to schedule jobs on the CPU fairly, in the sense that all of the jobs in the system get a fair share of the CPU. The second, with the introduction of the SMP systems, it was essential that the Linux scheduler have the knowledge of scheduling jobs across the CPUs as well. So in order to explain this slide, I will take up a simple example. Let's say you have 2 tasks, task A and task B in the system. Task A is will be to the left of task B in the red black tree, which happens to be the data structure representing a CPU run queue. And task A will be to the left of task B if it has received lesser CPU time than task B and would be scheduled next. But how do you know how much time has a task got on the CPU? This is measured by a metric known as the virtual runtime, or the V runtime, and this, along with the usage of the V runtime to place it on the red black tree, together determine the fairness of the scheduler. In fact, this is a separate topic in itself which would take another session, so I will be skipping briefing you more about it. So these are the goals of SMP scheduling. I will probably illustrate this with the next slide. So the first goal of SMP scheduling is very simple. So if you have a task to run and you have an idle CPU, schedule this task on that CPU. It's as simple as that. This nature of the scheduler is called the work conserving nature of scheduler. What it means is that if there is someone who is demanding CPU capacity and you have CPU capacity, just match them and get the job running as soon as possible. The second important goal of a scheduler is that you must not have any CPU which is heavily burdened. You can have idle CPUs, but not at the cost of overloaded CPUs. Therefore, when you have such a situation, it's essential that all CPUs get equal amount of task. So this is achieved, that is the even spreading of load across CPUs is achieved by an efficient load balancer in the scheduler, and the former goal which I mentioned about finding a CPU to run on for a task which has just come in is decided very much on how scalable the scheduler is. The reason is, if with a growing number of CPUs, if the scheduler takes a very long time to find an idle CPU to schedule the task on, it would heavily affect the interactivity of the workload and throttle the task. Therefore, this challenge is answered by scheduling domains and scheduling groups, which I will be explaining in another slide. And at this point, I also take up this point to introduce the power aware scheduler. So a lot of talks has been going around the power aware scheduler in the community today. So I will be speaking about what exactly it is, what it does, and why is it so difficult. An effort has been made towards introducing the power aware scheduler before also, sometime in 2006-2007 time frame. Even then it had trouble getting in. It got in and got out actually, and this time also a lot of efforts has been put in, and we need to see why it's so difficult for the power aware scheduler to get into the mainline. So the job of the power aware scheduler, to put it very simply, is that no matter what it does, it should ensure that this ratio increases, right, the power efficiency ratio. So primarily the primary ask of a scheduler, of a power aware scheduler, is that at least the denominator should decrease. I mean, that's why it's named so, but if it increases the numerator as well, then that must mean a warm welcome into the Linux kernel for the power aware scheduler. So why is it so difficult to achieve this? So before I get into the power aware scheduler and its implementation, it's essential that we understand this scheduling domains and groups. Firstly, because it also answers the scalability of scheduler, and secondly, it's important the power aware scheduler, the load balancer, and works in this hierarchy. So let me start again on a very simple note. Let's assume that you have a CPU with two hardware threads. The CPU comprises of the scheduling domain, and the hardware threads are beneath the scheduling domain, and each of them is a scheduling group. Now scale this up. So imagine there are multiple CPUs like this. So all of them will form an additional level of scheduling domain, with each CPU being a scheduling group. So this is how different levels of scheduling domain is built, one on top of the other, with each of them becoming a scheduling group in the next level. So the load balancer, the power aware scheduler, all of it work at each of these levels. So the load balancer, for example, ensures that the load is evenly spread across the hardware threads first, then it ensures it's evenly spread across the CPUs, then in between the CPU packages, and so on. Yeah. So let me reintroduce what the essence of the power aware scheduler is. So let's take another simple example. So if you have a scheduling group with one busy CPU, and you have a scheduling group with one idle CPU, what power aware scheduler does is brings that task on the busy CPU to the idle CPU of the other group, and ensures that that scheduling group is completely empty. So why does it do this? It does this on an assumption that each of these scheduling groups are powered independently. So if you empty one of them, they can be completely shut down and save power. I mean, otherwise this wouldn't really help, but we are assuming that each of these groups are independently powered, so emptying one of them, if there's only one task on it, would gain us some advantage, and that would result in a consolidation of load. So that's illustrated in this example, in this picture, and it's essential to know certain terminologies at this point: group leader and group minimum. So group leader is a group which has one idle CPU. Why is it called group leader? It's called so because it is responsible for taking tasks upon itself, and group minimum is a group which has just one idle CPU, one busy CPU, and it's called group minimum because it has to tell the scheduler that, look, I have very minimal tasks on me, please take it away from me. So the load balancer works exactly like this in the power aware scheduler. At this point, we can also try and understand what happens in these two scenarios: forking of tasks and waking of tasks. So anyway, when you fork a task, you would search for an idle CPU for it to run on. Why not do it on a group leader? Do it on a group leader so that you try consolidating load as much as possible, or you pack load on a group. When you wake up a task, you could do the same, but you can take an additional step forward. If you think that the task has been very dormant of late, then you can probably pack it at a CPU level also, and that CPU is called the leader CPU. So you first see if that task, which is very small in the sense it doesn't require so much CPU power, could be scheduled on a CPU which already has some other task running on it. If you can afford to do that, that would be great, because you would be consolidating at the CPU level as well as you would not be throttling that task, because it would anyway not demand that much power. So any questions so far? I hope I am being clear in my explanation, so if at all please do stop me. So the next question, I mean always this question is asked, why is how is power aware scheduler, isn't it a disadvantage because it's going against race to idle. So what is race to idle? Race to idle is you ensure that all tasks get evenly spread across the CPUs, finish the tasks quickly and be in an idle state longer. So being in idle state longer would yield you significant power saving. So isn't the power aware scheduler trying to consolidate the load, not doing this? The answer is the power aware scheduler does race to idle within a power domain, that's all is the difference. If the power domain gets overloaded, it will do a race to idle across power domains. So what this means is that the concept of race to idle is not getting lost in the power aware scheduler. You only decide to do race to idle within certain domains, that's all. So nowhere are you throttling tasks. Now I keep speaking about terminology like busy CPU and idle CPU. So what exactly is a busy CPU or an idle CPU? You would call a CPU busy if the tasks which are on that CPU you utilize that CPU till its capacity. Let's say the CPU has some capacity X, if all tasks use the complete capacity then it would mean that CPU is 100% utilized. So what is utilization then? So utilization can be explained with 2 points. One is if there is some task to run on a CPU all the time, it would mean the CPU is 100% utilized. That seems fair, right, because the CPU is engaged all the time. But if there is some portion of the time when there is no task running on that CPU, it would mean that the CPU is idle for that duration. But would you say that that is 0% utilization, or would you say that it's somewhere between 0 and 100%? If you were to say it's 0% utilization when no task is running, then why do we even need a percentage utilization metric? I would simply say that if there are tasks running on the CPU, then it's 100% utilized. If there are no tasks running on the CPU, it's 0% utilized. Why do you need a percentage utilization metric? What is the importance? I'll demonstrate that in the next 2 examples. So let's take up this. So CPU 1 has been idle for a long time, okay, and CPU 0 is running a task. The task finishes, T1 finishes, and CPU 0 just got idle. After a while there is a task that wakes up on CPU 1. Now leave aside power aware scheduling and everything that I spoke so far, and let's look at this situation independently. Now if there is a task on CPU 1, what would we try and think? So CPU 1 has been idle for a really long time, which would mean it has entered deeper idle states, right? Getting out of idle states has requires significant power. First of all, there will be a latency hit because it has to come out of the idle state. Secondly, there could be certain things to do before it comes out of the idle state, like cache flushing, which requires significant power. So what you would ideally do is leave CPUs which have been idle for a long time idle. Try to put it on a CPU which has just gotten idle, because chances are that it has not entered deep idle states. It can come out of its idle state very quickly. So we would want to move the task from CPU 1 to CPU 0, and that would be the final scenario, the last picture. So let's see if I were to use the number of tasks as my metric, which I will from now on call NR running. So if I were to use NR running to decide if a CPU is idle or busy, this would not have happened. Let's see why. So the power aware scheduler sees that CPU 1 has 1 task running on it. It would not try to do any load balancing, because doing so wouldn't result in anything. CPU 0 would get 1 task, while CPU 1 would become idle. It's the same scenario. Yes?
Instead of assuming that a CPU idle driver has left a busier CPU in a shallower C state than an idler CPU, would it be an idea to have the C state driver inform the scheduler? So you can actually know for sure.
Yeah.
It seems like a good assumption to make. It might make sense to know for sure and have the C state driver write the information in for CPU memory, so you can evaluate which one is in a deeper sleep state.
Correct. So this is the goal going forward. We would like to integrate CPU idle drivers and the scheduler together so that they can communicate and do better scheduling. That is not yet, we are not yet there, but going ahead we would like to do that. This is definitely on the plate. We would like the CPU idle driver to communicate with the scheduler and let it know if it's good enough to wake up the CPU or not. That's very important. So in this case, if I were to use NR running, what the power hour scheduler would do is just leave it on CPU 1. Ideally this would happen, but if it were to use percentage utilization, CPU 0 just got idle, so it had 100% utilization. That begins to decline. Maybe let's say when it comes to the third scenario, it's around 97%. CPU 1 was idle for a long time, its percentage utilization is 0%, and when task T2 comes, it begins to increase. When the power hour scheduler looks at the percentage utilization of both these CPUs, it realizes that CPU 0 could be a group leader, right, because its utilization is almost there at 100%, but it still has capacity to accommodate some task, and it would move the task from CPU 1 to CPU 0. This would not have happened if you were to use NR running as the metric. So I hope I conveyed the message here, but anyway I will take up another example to tell you all why percentage utilization is a better metric to use. So before I move on to that part of the slide, I would like to bring in an important aspect of scheduling which is not there in the current scheduler today, that is the behavior of tasks. Now tasks could behave differently, so let's take up the first example. If a task were to fork and till it dies, if it were to run continuously without sleeping, it would be a 100% task. But let's assume that this task has a period of 10 milliseconds within which it has a sleep wake up cycle. It sleeps for 1 millisecond, it's awake for a millisecond and sleeps for 9 milliseconds, and this nature repeats. So if I were to measure what kind of a task this is at the 10th millisecond, it would mean it's a 10% task, right, 1 by 10 into 100. So if I were to measure it within 10 millisecond, at 10 millisecond, I would get to know that it's a 10% task. Now look at the third example, in which the task sleeps for 900 milliseconds and is awake for the last portion of the time. I would know it's a 10% task if I made this measurement at the first second, at the end of the task. If I were to make it somewhere here in between, I would still consider it as a 100% task. Now why I brought this slide into picture is for you to understand how you determine if a task is X percentage task or not. And it's very important that you know when to measure it. For example, in the third one, if you were to measure sometime within 900 milliseconds, you would not know its behavior. For a scheduler, it's important for it to note what kind of a task it is, whether it's long running or short running, which I will explain later. But what is important for us to understand is that a scheduling period is 4 milliseconds. So within 4 milliseconds, whatever is the behavior of the task can be captured by the scheduler. So every time it measures, it makes its measurement at the 4th millisecond, and if such a cycle exists, it can capture it. So we should cache in on that nature of the on that functionality of the scheduler. Why I say that is, look at this. In this example, in the current scheduler, the way it works is CPU 0 has one task and CPU 1 has 3 tasks. The current scheduler would definitely say the second CPU is overloaded while the first CPU is not, because there are 3 tasks there and there's one here, so it's pretty obvious. It would try to move tasks from CPU 1 to CPU 0. But look at the way it would work if I were to use percentage utilization metric, if I were to use a percentage utilization. In there, CPU 1 is running 3 tasks, but all of them are 10% tasks. What this means is that the tasks are sleeping most of the time. So if the scheduler were to understand that the tasks behave that way, it would make a wise decision in moving the task from CPU 0 to CPU 1 for better utilization of CPU 1. Because anyway tasks on CPU 1 are sleeping for most of the time and is not using the CPU. why not use that CPU by moving the task away from CPU 0 to CPU 1. This is what happens in the power aware scheduler. It can easily understand that CPU 1 is a group leader and it can move the task from CPU 0 to CPU 1. This would not have happened were we to use the NR running metric. So there are two important points which I would like to bring in at this point. One is that measuring the percentage utilization of a task, the way a task behaves, is it short running, is it long running, is very essential for a scheduler to know to make wise decisions. And if we cash in on that aspect, if the scheduler were to know that and we were to cash in on it, we would make better load balancing decisions. And that's illustrated in the second example. Any questions? I mean, if you are unable to understand something also, please do stop me. I would be really glad to repeat it. So power aware scheduler currently in its present implementation makes use of the percentage utilization metric, and we would expect a better decision happening with it. So it would qualify a group as a group leader if its percentage utilization comes up to the CPU capacity. So that's how it makes it evaluates a group as a group leader or a group minimum. Now, so who is taking care of calculating this percentage utilization? The percentage utilization of task is currently not being calculated in the scheduler. At least at the task level, it's not being calculated. This advantage is brought in by the per entity load tracking metric. I'm sure many of you have heard of it. The PJT's metric, as it's popularly known, introduced by Paul Turner. He introduced a set of patches which brings this. Actually, it's currently in the main line. It's been upstream. The only thing is that it's not being used in the load balancing and power aware scheduling yet in the main line. So I would like to introduce the Paul Turner's metric here and brief you all about what exactly it is. So in the current scheduler as well as in the power aware scheduler, the CPU run queue utilization is being calculated. Both of them calculated. In the even PJT's metric does it, and the current scheduler also does it. The difference is that the current scheduler does not decay the history. What it means is it gives equal importance to the run queue utilization at all points in time in the history of the run queue, while PJT's metric doesn't do that. It ensures that the history decays and the foremost behavior of the run queue is given importance. So let me explain this with the previous example. So look at this. This was the slide I introduced to mention the importance of percentage utilization. Now CPU 0 was busy, okay, it got idle, so its percentage utilization was 100%, starts dropping from 100%. CPU 1 has been idle for a long time, its percentage utilization starts increasing from 0% upwards. If I were to, okay, so let's assume that CPU 0 was idle before this scenario, it was idle, now it got a task, and then the situation continues. If I were not to decay the history, probably that idle period of CPU 0 would override the just busy scenario of CPU 0. And if CPU 1 was busy before but is now idle, that the busy history would probably override the just idle scenario. And it would not probably make that decision. It would probably conclude that CPU 0 has been idle for a long time and CPU 1 is busy for a long time and would not take that decision. So it's essential for us to, I wouldn't say essential, so what I mean is this is one of the advantage that PJT's way of calculating the CPU run queue brings onto the table. So the foremost behavior of the run queue is given more importance than long ago. So, and another advantage that it brings in is that the distance between these arrowheads is wider for the current scheduler, and in the PJT's metric it's 1 millisecond. So it's calculated at a much finer granularity, and by doing so he has proved that this has resulted in much stable behavior of workloads, because the scheduler is able to correctly judge the run queue utilization at any point in time. I hope I have succeeded in convincing you that the PJT's metric and percentage utilization itself brings a lot of advantages to the scheduler. If that's the case, I would like to take this opportunity to tell you that there are some disadvantages also to the PJT's metric. Let me illustrate this with an example. So if you have a scheduling group with 4 CPUs which has been idle for a long time, and all of a sudden each of those CPUs get one task each, okay. So the percentage utilization of this group was 0%, has to climb up to 100%, right, for it to reflect that 4 tasks have come on that group. But it so happens that this climb from 0 to 100% takes a very long time, and the scheduler should not confuse this socket as being idle. So it has 4 tasks on the 4 CPUs, but the percentage utilization does not reflect that. It takes time to pick up, and if it takes time to pick up, the scheduler should not put more tasks on that socket because the percentage utilization is less. Taking a mirror example of it, if the socket, if the group has 4 tasks on it and all of a sudden all of them finish, then the CPU, the percentage utilization has to decline from 100 to 0, and it takes some time. Within this time, if the scheduler assumes that the group is loaded, then it would not put any tasks on that socket, on that group. So because it takes time for the utilization to pick up or to drop, it would result in incorrect decisions by the scheduler, and therefore after a lot of discussions in the community, we sort of came to a conclusion that if there is a steep increase or decrease in load at any point in time in the system, it's best to use the NR running, the number of tasks metric, that would rightly reflect the load on that group. But if you have a stable load for a relatively long time, it's best to use the per entity metric, because that would actually be more accurate than the NR running. So Alex Shee from Intel has posted out this patch set very recently, and a lot of debates have been going around it. There are a lot of aspects around which we had our discussions. The first few, which I have already mentioned in the slide, the usage of the metric, where it fell short. Now coming to scheduling policies, so there was a debate around whether you would like to consolidate tasks at the CPU level also, that is pack across hardware threads. If you were to do that, you would gain certain disadvantages because there is contention of resources between the hardware threads, and you would not like to consolidate at that level. But sometimes consolidating might also help if the tasks are sleeping most of the time. So in their sleep cycles, the other task can use that CPU. Anyway, so that was one of the points of debate, and the last point also I have mentioned in the slide. So after all this, actually a lot of improvement did happen in the code and the design of it. The reason I say this is that in 2006, when Power Aware Scheduler was introduced, it had certain disadvantages. The first being, it was not using a metric like Paul Turner's, it was using NR running. So it was not very convincing the way its results showed up. The decisions could have been incorrect. Now that we have a better metric to do the scheduling, and it's being used in Alex's patch set, this would be a good step forward, and we should make use of this opportunity. The second reason why that failed in 2006 was that it had a lot of tunables at every scheduling domain, but that doesn't exist in the current implementation. So as it stands today, it looks positive, but then why is it so difficult for it to get into the main line? Now, as it was mentioned in an LWN article by Jonathan, we are touching a very significant part of Linux. Scheduling is a very core part of Linux, and if we try to change its behavior like now, like the way we are doing now, the maintainers don't really like it, nor do the developers. They would like very good experimental results to back it up. They would not want any regressions in the scheduler, and to evaluate whether any of this will happen, any regressions will happen. Scheduling is such a complex giant that you would have to run a lot of workloads on a variety of platforms in different scenarios to completely convince people that we are not causing any regressions. So that is why it's becoming very difficult for it to get into the main line, but looking at the current discussions around it, it's in a much better shape than before. So we hope to do our best to get it into the main line as soon as possible. And in this slide set I have made some effort towards evaluating the power aware scheduler on an experimental basis. So the first is the behavior. Now, is the patch set correct? What it means is it consolidating load at all, or is it just in the theory? The second is, if it is consolidating load, I would like to see some changes in the power efficiency. So is it showing any positive results over there? So this graph showcases the way eBusy as a benchmark behaved on an x86 machine, which is a 2-socket 8 cores per socket machine. On the left hand side you can see that as long as there are 8 threads which are being spawned by eBusy, which will occupy the one entire socket, there is consolidation of load seen. So you can see that in the graph. And just to prove the point, I have compared it against what happens in the current scheduler, and you can see that that's not the case. The load gets evenly spread, almost it gets spread across the sockets, and there is no consolidation. And this is with kernbench run on the same machine, and I see a similar kind of behavior. So the y-axis is a percentage idle time, so 100% would mean 100% idle. And this is the eBusy run on a power machine. It's a 2-socket 8 cores per socket SMT4 machine, and again here you see that as long as you spawn threads which is equal to the number of cores in a socket, there is consolidation of load. But once you spill over, power aware scheduler falls back to the default scheduling mechanism and ensures that both sockets are occupied. Again you can see on the right hand side that the current scheduler does not do this. This is the result with kernbench on the power machine. So I could see a consistent result in terms of the behavior of the power aware scheduler. It was consolidating the load, so I would expect some amount of power efficiency. So the next slide actually showcases this. So the left hand side is an eBusy run on an x86 machine, and the right hand side is a kernbench run on an x86 machine, and I have normalized the behavior against power aware scheduler, and it can be seen that across the number of threads that I have run this benchmark on, the power aware scheduler fares better in terms of power efficiency. So these were some of the experiments that I ran, and I would like to sort of bring a conclusion to this aspect of scheduling by saying that we seem to be going in the right direction. The only point that remains to be proven is, are we causing any regressions which has gone unseen or unnoticed by any of us. From a theory standpoint it seems right, except for of course certain details in the power aware scheduler which we need to take care of. The overall structure seems fine. At this point I would like to introduce my last topic, the other efforts that are being made in towards increasing the power efficiency of the scheduler, and one is the most spoken about ARM's big little CPUs. So it's very simple. So big and little are just that more CPU power and lesser CPU power. So you can make use of this platform if you know how to identify tasks. Currently in the scheduler that's not being done, and the Paul-Turner's metric brings in that advantage to the table. It's able to identify a task as long running, short running. A short running task would ideally be fare better if it's run on a little CPU, and a long running task would fare better if it's run on a big CPU. And now that we have the Paul-Turner's metric, it's being cashed in on, and this has been released in a patch set by Morten Rasmussen from ARM, and discussions have been going around it. And Vincent Guitart from ARM has also released a patch set which does packing of tasks. So the essence of the scheduling of this patch set is that you identify certain power domains as taking on the responsibility of running short tasks, so that the other power domains can be put to sleep all the time. So some power domains are only responsible while the rest are not. By doing so, so how do you identify short running jobs? Again, is through the Paul Turner's metric. So this is another effort which is being made in this direction. So that's about what I have for today. And the first set of references that I have is wherein in the first, yeah.
Oh, you can go through references.
Okay. No, I just like to mention one point here. That is the first, initially there were efforts made towards integrating per entity load tracking into the load balancer itself. Not the power aware scheduler, into the load balancing itself, and to see what kind of an effect it would have. Was it causing any performance differences over the current scheduler? And the rest of the references refer to the discussions around power aware scheduler. Yeah.
So I was just curious, is the expectation that this will be the default policy, and if so, have you guys are you working towards or planning on working towards working with the NUMA balancing aspect and maybe taking the RSS size as a hint for long-running tasks and looking at the latency hop across domains? Because I mean, when you're talking where your power domains are potentially at the level of multi-node sets, you know, then packing a task could have, you know, huge consequences both on the task as far as the raw latency hit to its performance, but also all the work to move all those pages later on due to the NUMA balancing. So, you know, I'm assuming you guys are thinking about that and working towards it. I just was curious if you could say anything.
Yeah, sure. So if I were to rephrase your question, it's about if you are consolidating loads across NUMA domains, you would have you would probably there would be a disadvantage in terms of cache.
There should be a weight there, basically.
Yeah, there should be a weight. Yeah. So that is definitely a matter of concern. Is the first point. The second point is consolidation of load will definitely hit this problem. Okay. And I would like to explain this in two scenarios. Firstly, when tasks begin to fork, they start forking on one NUMA domain, and then they spill over. So till the time it spills over, if you try and consolidate load over that NUMA domain, it's perfectly fine, right? When it spills over and then you try to consolidate load, you would definitely hit a problem wherein those tasks would have their pages in the cache of that domain, and you would try to pull it and you would lose the cache benefit. Because
it's not just the cache benefit, it's also the memory controller host. But yeah, I mean, I'm worried about the cross-bus traffic as they start instantiating pages on their new home node.
Okay.
You know, and then if they get packed back to the original node or some other node, you know, the NUMA balancing will then start migrating the pages between memory controller DIMMs to try to bring them back to the home node, and that's a lot of work for the kernel that it has to do.
And power.
In the meantime, you take the latency hit of fetching those pages into the new cache.
Correct. So there's so when it starts to spill over, this problem comes in when the tasks begin to spill over. So the discussions have not touched this point yet, but I would like to say that in the current scheduler itself there is a fix for this. Whenever it tries to migrate tasks from one power domain to another, it ensures that it moves the tasks which are cache cold. There is this check already in the scheduler. So if at all you were to spill over the power domain and try to consolidate, like the way the power aware scheduling is doing now, it would consolidate only that load which does not, which is cache cold and does not have significant number of pages in the cache. That check is already there in the scheduler. But this is a point that we have to definitely concern ourselves with. But we have not begun discussions around it yet.
So one of the problems that certainly we've had upstream is benchmarking and identifying regressions in scheduler performance. I'm thinking most recently of the big PostgreSQL problem that was only discovered around an RC6 timeframe. So I saw in your benchmarks that you were using KernBench. What other kinds of tests are your group running to really determine whether these things changes are a win across all sets of tasks, or these minimized regression?
Oh no, the two benchmarks that I've run don't test all kinds of workloads. KernBench is essentially short running jobs, and eBusy which I ran was simply long running. So I had just two benchmarks, one with just long running jobs, one with just short running jobs, and while I was performing experiments I used to combine both and check. So these are the only kinds of workloads that I have run. yeah, there's definitely scope for more experiments. Yes.
I'm not sure if it's different from the regular scheduler or PM aware scheduler. It seems like PM aware scheduler favors totally not idle CPUs. That means, is that correct? If it's in totally idle state, then it would favor the one that's not in a deep idle state.
So you are saying that it won't touch the completely idle CPUs, but would probably schedule tasks on an almost idle.
I was wondering, how would you ensure if if my conclusion from your talk is correct, that it would favor the ones that are harder than the coldest set. How would you ensure that you're not taxing a certain set of CPUs?
Oh, okay, okay.
The others.
Okay, so.
Not for miles on some CPUs and not on others.
So when I so in this yeah, so when I say that it's a group leader and that I pull tasks from an idle CPU over to this group, I am not overburdening any CPU. So each of these is one CPU and each of them get one task. They don't have two tasks on each of these CPU. So the way scheduler is designed today is that it considers a CPU overloaded if there's more than one task on it. So if I try to consolidate tasks from that socket to this and make that idle, I would not be taxing any of the CPUs here because I would be scheduling that on an idle CPU and not on a busy CPU.
I am referring to another slide which shows that you had CPU 0 and CPU 1. CPU 1 in a deep idle state and CPU 0 was, there is another slide that you showed.
Yeah, I just come to
when
that.
you're talking about favoring the CPU that's not in a deep idle state.
Okay, yeah, I get that one. Yeah. Okay, regarding this slide.
Right.
Yeah.
So
Okay.
here you were talking about over there.
CPU 1 is
right.
in a deep idle
CPU1
state.
is in a deep idle state
Yeah.
and CPU 0 is not.
Yes.
So you were talking about, when you talked about scheduling 2, you talked about putting it probably favoring CPU 0.
Yes.
Would that result in taxing certain CPUs over the others?
No, it wouldn't. Anyway, that task would have to be scheduled on a CPU. You might as well choose a CPU which wouldn't take a lot of time to come up from idle. You would have to tax one CPU at least. You would try to tax a CPU which would take that task on quickly. So if you're thinking that you're keeping CPU 0 busy all the time and that would mean taxing, I wouldn't say that.
Well, it kind of is, but you might have a set of CPUs that are in deep idle state that would not be used.
That's perfectly fine. As long as you're not throttling tasks and CPU 0 doesn't have more than one task, it's perfectly fine. I mean, it's not like if you're keeping CPU 0 engaged all the time, it would be taxed. It would be taxed, CPUs will never be taxed, in the sense tasks will be throttled, in fact. So if you have 2 or 3 tasks on CPU 0, you would be throttling those tasks if you're not using CPU 1. But if you have just one task to run on, you could schedule it on a better CPU. You would not be taxing it. Yes.
So just to clarify, it looks like this plays a role in deciding which CPU runs on when there's idle CPUs available. It seems like if the run queue is more than one deep on all CPUs, then this falls back to the completely fair schedule.
Yes, it does.
And so that's kind of the unpacking mechanism.
Yes.
You pack up things, but if the run queue gets longer than
right,
then
you will have to split. So if any group gets overloaded, you will fall back to the default mechanism. So that's why I said it's raised to idle within a power domain as long as you can afford it.
How does it affect performance for the lightly loaded scenario?
How does it affect, sorry?
Performance. So if you load only one processor and the other is idle, there is less resources like caches and so on. So it must degrade the performance.
In what scenario again? Can you repeat that? In what scenario would it degrade performance?
So the current scheduler distributes the task across
Right.
processor and makes it because there are more resources available.
Right.
Like level 3 cache.
Yeah.
And if you
Consolidate.
consolidate, yes, you degrade performance.
Okay, so you're
Have you
saying.
done any measurements on how it affects performance?
Okay, so the question would be that if you consolidate load and your cache is not big enough to handle the pages of all the tasks on it, it would result in a lot of cache swap, page swapping, right? Well, we haven't. So that's why I probably have to say that you will have to run a lot of experiments to ensure that such things are not being done on all kinds of workloads. It depends on the workloads. Your question is around the kind of workload. If all tasks are sharing the pages, then even if you consolidate, the size of the cache doesn't really matter because they all use the same set of pages. But if they're using independent pages and you try to consolidate, it would result in swapping of pages. That's true. It should happen if at all I try to consolidate. But I have not performed experiments to verify that. But we should, ideally. So this is why it's so difficult to bring in changes into the scheduler, because there's so many workloads to take care of and you don't really know if it will affect it.
And there are other kinds of resources, for example, in hyper-threaded
Right. So we don't try to consolidate to hyperthreads if at all it results in performance degradation. At least in my experiments I have totally avoided that. But sometimes it could be useful. So that's another thing we need to take care of.
There's a related issue where some of the CPUs have lots of cores in them.
Okay.
They can run a few of the cores at a faster than normal frequency, turbo mode. But
Right.
if some of the other cores are idle,
Huh.
that's in a package. It's somewhat related to the hyper-threading issue.
Okay, so
Yeah. That also would affect the raise to idle thing.
so how would it affect in this case?
If you consolidate all the workload onto the cores of one CPU,
Okay.
none of those cores can run in turbo mode, and the
Okay.
workload will take longer to complete, and it will take longer to reach idle.
Okay, I probably have to think about that. I'm not too sure. Right.
I mean, a lot of this discussion is around the power per watt, right? The
Right.
efficiency of the CPU, like the cache utilization. I mean, some of those things you can already measure today and include in the process context somehow with the DF-mon or perf-mon or whatever it's called now, the CPU perf.
Okay, perf.
Especially IBM has that in their power processors, and x86 has it as well. Has anybody tried to look at that to integrate the efficiency? For example, you could look at cache miss rates when you move a process. Does the cache miss rate stabilize at a different level than it did before?
Okay.
Right? That
Okay.
kind of historical view of how efficient is the process running when it's been moved or when after you moved it.
Okay. Well, I haven't really tried this, but
No, I mean, has anyone done that?
no.
I mean, that would be similar to we were talking about the the turbo mode. You can do a similar thing. You can see how many cycles, how many instructions per cycle am I getting?
Okay.
Right? That sort of average over time.
Okay. In the current discussion, at least, we haven't begun on this aspect, but going ahead we should, because you're right. There are so many problems that we still need to take care of. One is the cache benefits that we will probably hit if we consolidate. Second is the turbo mode that he mentioned, and the third, you're right. We probably need to look at the process more closely.
I'm just saying there's hardware monitoring available to help you measure runtime, help you measure with no impact on performance, or very little impact on performance, the cache effects, for example.
Okay.
And you can see how much, because cache miss rate is usually a pretty good indicator of whether you're thrashing, and that is going to have a huge impact on your efficiency.
That's true. Yeah, we should do this. We know that we will be affecting cache performance, but we haven't touched that aspect yet. We should, going ahead, we should. And good that you pointed out this.
I think it's a similar issue to somebody mentioned page migration between NUMA nodes.
Right.
And that's why they've always had sort of an affinity, a CPU affinity number for every process. That's why it sort of sticks to a CPU for
Right.
a while because of the cache affinity. I think you might have a NUMA affinity associated with it as well.
Yeah, this happens actually. In the current scheduler itself, it takes care of that. It it checks for the CPU affinity before it migrates the task. Anything else? So yeah, so that's it from my end. Thank you very much.